All right, good morning. So let's keep working. Let's keep moving on through Calc 2. So last time we covered, or rather we finished section 3.11, hyperbolic functions. And well, today we move on to a whole new chapter, which is chapter 6, and it's about applications of integration, which in a way you did a little bit of it already, even though not necessarily as an application for areas, but rather we use the idea of area under the curve in order to construct the integral. That is, what we did in Calc 1 is to given a function and its area under the curve, to partition it into a number of rectangles and add the area of those rectangles to find, well, just an approximate area, not actually the area, but well, then we introduce the concept of Riemann sums, which are related to limits and infinity, in order to find infinitely many areas of those rectangles, which actually give us the actual value of the area. I mean, of course, we were not going to compute infinitely many areas by hand. We used the idea of a limit at infinity to do that. Well, the picture for that is the following. A function f of x, call this f of x, and from a to b, and that shaded area right here, right, can be found by the integral from a to b of f of x with respect to x. Okay, and so that's basically what the definite integral gave us as a result from in Calc 1, right? But then you didn't really look at these exercises as, oh, this is the area under the curve. Maybe yes, but more in depth, we do that today. Okay. Well, so the difference between calculus and algebra, or basic geometry, we had formulas to find areas of rectangles, length times width, and the areas of triangles, well, depending on the type of triangle, an equilateral triangle, a right triangle, etc. There's different formulas. But when it comes to finding areas of a shape like this, from A to B, because we will find the area of something like this, of what we're looking shape. For basic shapes like a rectangle, we can just use a ruler, measure the dimensions of the screen, length times the width, and multiply the two numbers. Unfortunately, for weird looking shapes, we don't have like a curvy ruler to, well, maybe some designers have some, but I mean, there's a really big number of curvy shapes that do not fit every single ruler. You would have to design a ruler, a special ruler, to find those dimensions, and still it's hard. So in this case, what we do is represent those curves as functions f of x and use the integral to find that area under the curve. Well, so in this case, we want this area defined, or rather bounded above by some function f of x, and bounded below by another function that we call g of x. Okay? Well, how do we find this area using integrals? Because this is not just the area under the curve. This is the area between two curves. Okay? So, this is the same as saying, well, how about we find the area of the top function from a to b, and we subtract this little gap right here. That is this big area right here, this little area right there. Alright, and again, let's keep labeling this. This is F, and this is G. Okay? If we were to set the area of this region bounded by F and G, that'll be the integral from a to b of the top function minus the bottom function. And in this case, the top function f of x minus g of x. And well, you might want to label this as top minus bottom. You know, in this case, to make our lives easier when it comes to defining or to interpreting the region of integration that we're working on. All right. So that's our general case, of course. I mean, that's the case that we're going to use for most of the examples in this section. However, there will be situations in which we will be in the need of twisting the whole problem in a different setting. So for example, we can also define that's an f of y and a g of y. All right, and also go from not from A to B anymore, but in this case we're gonna go from C to D. All right, you'll see how in a problem later in the section we'll have to twist it in this way. And well, of course, I mean, let's set up the problem. Area will be the integral not anymore from A to B, but rather from C to D of, in this case, we're not going to go the top minus bottom, we're going to go the other way around, the horizontal perspective in this case. Rightmost minus leftmost. What do we do that? Well, I mean, think of comparing the height of two buildings or two people or two structures. We always subtract the smallest from the largest, right? Because we want a positive result. We never do it the other way around to get a negative result. And for place as well, we always find the distance of the furthest place and subtract that distance from the closest place to get a positive difference. So that's why we go rightmost minus leftmost in this case. So, and the rightmost in this case, which is f of y minus g of y, which is the right minus leftmost. And then in this case, with respect y. And again, let's label this as rightmost minus leftmost. All right, rightmost minus leftmost. Well, of course, I mean, this is everything in symbols, very generic images. How about we see this in action with actual examples involving some functions and numbers, etc. Okay, so example number one, a good example as a warm-up where everything is given, everything is explicitly specified. You know, they're asking us to find the area of the region bounded above by y e to the x, y equals e to the x. Well, they're telling us that that's the top, and bounded below by y equals x, they're telling us that that's the bottom function. And they're also giving us the limits of integration bounded on the sides by x equals 0 and x equals 1. So, but still, it's important to sketch the region, of course. Well, number one, for practice, because we're going to use this in the subsequent examples. And well, the graph of e to the x, it's an increasing graph. It's a function that grows with a y-intercept at 0, 1. And then we also have the diagonal line y equals to x, passes through, it's a straight line that passes through the origin, right? And well, the bounds, the horizontal bounds, that's going to be from x equals to 0 to x equals to 1. So ultimately, we're finding this shaded area right here. So far, so good? Okay, so again, even though they are very, very explicit about what the top function and the bottom function, for the sake of practice, let's draw this representative rectangle right here. You don't have to do this every time you set up a problem. If you can easily see which one is the top, which one is the bottom, that's fine. But this is just an extra visual aid to easily see which one's top, which one's bottom, okay? So, area equals the integral from a to b of f of x minus g of x. So that's the formula. We already explained where it comes from. How do we set it up? And well, let's just put labels to this. In this case, the top. Oh, that's the limits. First of all, that's from 0 to 1. That's e to the x minus x with respect to x. And well, to evaluate the integral, there's really no need of any fancy method, like not even a substitution. It's just basic rules, you know. So the integral of e to the x is itself e to the x, and the integral of x is x squared over 2. And that is evaluated between the limits 0 and 1. Okay? We're essentially done with the calculus part of the problem. The rest of the problem is applying the fundamental theorem of calculus, which is evaluate the antiderivative at the upper limit minus evaluate at the lower limit. Okay, so that's e to the 1 minus 1/2 over 2, minus 1 squared over 2, minus e to the 0 minus 0 squared over 2. Well, e to the first power is simply e minus 1 squared over 2, which is simply 1/2, and minus e to the 0, isn't that 1 minus 1, and well, this 0 squared over 2, it's just 0. So we are essentially done. Combine negative 1/2 minus 1, e minus 3/2. And that's an exact answer. Of course, it depends on the situation. You might be asked to write this result rounded to 2 or 3 decimal places, but usually problems like this are in exact form question.
What if the curves like intersect in the region that you're finding the area for?
That's the next exercise. Yep. That's the next exercise. So again, this is like, you know, like possibly the easiest type of question in which everything is explicit, everything is given, just ready to boom, boom, put functions, put numbers, compute, simplify, we're done. Next one, however, it's a little bit more cryptic because, well, they're telling us, number one, find the area between the curves y equals to x and y equals to 6 minus x squared. That's all we know. Alright? Nothing more, nothing less. They're not telling us which one bounds above, which one bounds below. They're not telling us either the limits of integration as well. So it looks like that's what we have to figure out. So, but number one, okay, y equals x. Well, we already used that function. That's the diagonal line that passes through the origin. But what about y equals 6 minus x squared? What kind of graph is that? It's a parabola that opens down. How do we know it opens down? The negative leading coefficient, right? Even though it's not written in order, but I mean, if we rewrite it in descending order, we would have negative x squared plus 6, right? And yes. So, all right. So let's start sketching the region of integration. So we have an upside down parabola with a y-intercept at 6. That's really what it is. So y equals negative x squared plus 6. It's an upside down parabola shifted 6 units up. And on the other hand, we have this diagonal line. And well, coming back to your question, this is the situation right here, right? So they're telling us it's bounded by those two graphs. All right, so let's shade the area. And well, in this case, I think with this visual we can see which one is the top function, which one is the bottom function. But another piece of information is the limits of integration. And how do we get those limits of integration? Set equal to each other. Set these two equations equal to each other. That's going to give us the intersection points between the two curves, and therefore we're going to use those as our limits of integration. Yes, correct. Thank you. So we set these two quantities together. X x equals to 6 minus x, because they're both equal to y, therefore those two quantities are equal as well. And so x, whoops, no. Yep, not highlighter. And so point of intersection, so that's going to be x equals to 6 minus x squared. And well, in this case we solve this polynomial equation by factoring, well, because that's a degree 2 equation. If otherwise it were a linear equation, just solve for x directly, right? So let's see, when we have a polynomial equation with terms on both sides, you might want to have everything on the left hand side of the equation. Let's send the negative x squared with positive sign, plus x, and then minus 6. And then from here we need to choose the best methods to factor the trinomial, right? There's or whatever the polynomial. We can have like a special product, like sum of difference of cubes or difference of squares, trinomials, factor by grouping. In this case it's a trinomial, and in particular this trinomial has a leading coefficient of 1. So in this case we use what I usually call the double bubble method. We have two bubbles here, have the x's here, and then find two factors of negative 6 that add up to the middle coefficient, which is 1. What are those two numbers, by the way? So plus 3 and negative 2. Of course, one of them has to be positive, the other negative, so that the product is a negative number, and still taking care that the middle coefficient is a positive number. Well, zero product property tells us that x equals to negative 3 or x equals to 2. And voila, we have the limits of integration. Those are the intersection point, therefore the limits of integration. So after doing this algebra here, we may go back to the calculus part of the problem, which in this case is the setup of the integral. So area equals the integral from a to b, top minus bottom, that is f of x minus g of x, with respect x. I don't know, okay, yeah, x. Well, again, from the picture, which function is the top one? The parabola, and the limits go from negative 3 to 2, and so that's 6 minus x squared, and then minus the bottom, which is x. And again, well, in this case this looks just like a very raw polynomial. Let me do some labels so when you see this recording again, you see what this each represent. In this case, the top and the bottom are g of x, right? So that way no mysterious at all when you review this. Okay, so well, typically I prefer to have everything in descending order of powers, which is what I'm gonna do. Negative x squared minus x plus 6 with respect x. And again, this integration should be really simple. General power rule, negative x cubed over 3 minus x squared over 2 plus 6x evaluated from negative 3 to 2. And even though this looks like very simple, and in fact it is, however, I would like to go through all the details at least for this exercise, because there will be a lot of going back and forth with signs. You will see what I'm talking about in a second. Well, so the rest of the problem is fundamental theorem of calculus. So that is negative 2 cubed over 3 minus 2 squared over 2 plus 6 times 2. And then minus the evaluation at the lower limit, which in this case, this is the part where we need to be very careful. Check this out. So that's negative. Notice the lower limit is negative, includes a negative sign. I would open parentheses here. Minus negative 3 squared over 2 plus 6 times negative 3. All right. Well, I'm thinking the first group of parentheses is no big deal. It's really not that bad. So that's going to be negative 8 over 3. So 2 cubed, which is 8 over 3. Let's leave it at 8 thirds. And 2 squared, which is 4. 4 over 2, that's 2. 6 times 2 is 12. All right, that's the first group of brackets. I've just turned it into parentheses this time. Okay, let me go in slow motion in this second group. So number 1, the first term. We have this negative 3 being cubed. That is, it's being raised to an odd power. What does that become? Still negative 27 because of the odd power, but in this case because of the negative in front of it that came from the term in the integration becomes positive, right? So that's 27 over 3, which reduces to 9. And then over here, negative 3 quantity squared becomes positive 9, but because of the negative in front, goes back to negative 9 halves, right? And 6 times the negative 3, negative 18. And well, I mean, the rest we can use a calculator, get these numbers. After simplifying the first group of parentheses, we should get 22 over 3 minus the result of this should be negative 27 over 2. And the cheesy smile rule is going to jump in here. Combine the two numbers, we should get 125 over 6 as a final answer. All right. All right. So example number 3, we will have a twisted situation here. You'll see how this is going to work. Well, so what do we have? They are asking us to find the area between the curves y equals x cubed and y equals to x. So the y equals to x is there again. And in this case, they're specifying the intervals 0 to 2. All right. Otherwise, well, number 1, the graph of y equals to x is just a diagonal line. But what's the graph of the y equals x cubed?
It will go from the bottom and curve toward.
It's like an S, right? And it's an increasing graph, right? So it's going to look like this. All right? Sort of like this. But okay, check this out. Let's forget about the problem for a second. Notice in this case how many intersection points do we have? We have one right here, we have one right there, and we have one right there. If we were asked to find the area bounded by the two graphs without the 0 to 2, well, then we would have to set the area of area 1. Let's call this area 1, and let's call this area 2. That'll be area 1, the integral from whatever number to 0, for example. Let me just call it a. Okay, and that'll be the top minus the bottom, which in this case it's x cubed, minus the line, which is x. And then this second area, notice how the top minus bottom reverse this time. So in this case we have the top to be the line and the bottom to be the cubic. All right, and in this case that's going to go from 0 to whatever that intercept is, right? But in this case they're not asking us to include this little area in the integration because they're asking us from 0 to 2. Nevertheless, we will set this up in terms of two integrals because, well, you'll see why in a second. Well, first of all, we need to determine what the limits of integration is, and we do that by setting the two equations together and finding the intersection points. So that is, I'm going to set x cubed equals to x and solve the polynomial equation for the variable. Now, what's a good technique or a good strategy to solve this polynomial equation? GCF. Or how about divide both sides by x? Okay, be careful with that, because if we divide both sides by x, that's going to be x squared equals to 1. And well, we end up with a quadratic equation. How many solutions is that going to give us? 2. And if you look at the region of integration, how many intersection points are we supposed to get? 3. All right? So, and also there's another issue with dividing both sides by x. We would be potentially dividing by 0, and you know the whole story of dividing by 0, right? That's a non-defined. So no, in this case we need to move everything to one side of the equation. X cubed minus x equals to 0. Factor by the GCF, in fact, x times x squared minus 1. And what about this x squared minus 1? Doesn't that look like a difference of squares?
Can be factored.
Yep, we can further factor x times x plus 1, x minus 1. Alright? Now, we're going to get the 3 solutions. Alright? Which is consistent with the picture here, 1, 2, 3 points of intersections. Right, so that's x equals to 0 by the zero product property. That's x equals to negative 1 and x equals to 1. Okay, so this also confirms the second issue I talked about, you know, of potentially dividing by 0, because in fact one of the solutions is 0, and well, we cannot divide by 0. Okay, we're done with this algebraic part of the problem. So this means that, okay, let's label those points of intersection. That's x equals to negative 1. That's our x equals 0. And this is our x equals to 1. However, we are asked to integrate from 0 to 2. Right? So from 0 to 1, and then 1 to 2, well, so that's going to be actually 2 areas right here. Like I mentioned before, ultimately we will still finding 2 areas. Okay? So area subscript with a T to denote that this is the total area combining area 1 plus area 2. And then in this case the setting is that for area 1, the top function is one function, it's a linear function, and the bottom is the cubic. But when we integrate from 1 to 2, the whole problem gets twisted, and now the top function is a linear function and the bottom function is the top is the cubic and the bottom is the linear. So let's set up the integral. Area 1 from 0 to 1, that's the line minus the cubic with respect x plus the integral from 1 to 2, and that's in this case the top function, which is the cubic, minus the line, which is the bottom function with respect x. Up to this point, are you guys following me here? Yes? So far so good? Okay, so the rest of the problem is computing these 2 integrals. How about that? Well, again, general power rule, that's x squared over 2 minus x to the 4th over 4. That's the first integral from 0 to 1, plus the second integral, x to the 4th over 4 minus x squared over 2 from 1 to 2. Okay? So let's do fundamental theorem of calculus twice, one for each group of functions. Okay? And well, so this is going to be 1 squared over 2 minus 1 to the 4th over 4, and then minus, and let me make a quick comment here. So did you notice what happens when we evaluate this lower limit of 0 at both terms here? What's that going to give us? 0. So in this case, you don't have to show 0 squared over 2 minus 0 to the 4th over 4. Just write down a big 0. That's acceptable. And in fact, that's what I will be doing for the rest of the semester to save time. And that's something I encourage you guys to do when doing your homework, when working on a quiz or an exam, to save time. Of course, I mean, if you still prefer to write the whole thing, that's fine. All right? and then that plus 2 to the 4th over 4 minus 2 squared over 2, and then minus lower limit, that's 1/4. I mean 1 to the 4th over 4 minus 1 squared over 2. Okay, and let's just simplify this. So this is going to be 1/2 minus 1/4. But well, to combine these fractions together, isn't it that 1/2 the same as saying as 2/4? And 2/4 minus 1/4 is 1/4. 1/4 minus 0, so that's what remains from the group of from the first group of brackets here. But over here, it's going to be nicer numbers. So 2 to the 4th power, which is 16. 16 over 4. 4. 2 squared, which is 4 over 2, is 2. And then minus 1/4 plus 1/2. Careful with signs. When we distribute this negative over here, becomes negative. And when we distribute this negative over the second term, the very last term becomes negative times a negative, which is positive. All right. So, well, after combining these numbers together, well, we should get as a final answer 5/2. Okay. You can verify this using a calculator, of course. Yeah. Let me scroll this so you can see the whole thing. Question?
On the test, are we going to have a calculator?
No. You will be given problems that do not require heavy calculations, like simpler numbers. Mostly, I mean, you will be being tested on how to set up how to sketch, how to set up, and in some cases, you wouldn't even be asked to compute the integral. Just set up an integral, because you will be getting weird and crazy functions that may not even be integrable with the methods that we know so far. Okay? So that's a good question. All right, let's move on to the last exercise. Exercise number 4. All right, so what about this one? So find the area enclosed by y squared equals x plus 2 and y equals x minus 4. And by the way, there's a little typo here. This shouldn't be here. The x equals to 3 shouldn't be there. Okay, so for those of you who have the paper or the PDF, this is a typo. All right, so sketch the graphs and see how we set up the integral. However, one of the functions here, in particular this first one, y squared equals to x plus 2, it's actually not a function, if you notice, right? Because if we solve for y, we're going to get this plus or minus. We are going to have two different outputs for the same input, x. Well, even though it's not a function, well, there's a way around. You'll see. Number one, y equals plus or minus the square root of x plus 2, which is negative x, the square root of x plus 2, and the positive square root of x plus 2. So we have the two parts, the negative part and the positive part, and we are going to use this information to have a better idea on how to sketch the graph. All right, so let's set up our region of integration. And well, this radical function, well, let's forget about the negative verse. Let's look at the positive one for a second. This is the radical function, but in this case, the plus 2 is telling us that the curve is shifted to units towards the left. All right, do we agree with this? So, like this. And this is how the graph of a radical function looks like. Then, well, the same graph, the same function, but what happens when we have a negative sign in front of it?
It simply reflects off the x-axis.
Exactly, reflects it about the x-axis or flips it upside down, right? So, in a way, well, what about y equals x minus 4? Well, we're going to have this line right here, all right? with a y-intercept at x equals at y equals to -4. That's below the x-axis. So that's the region of integration. Whoa. All right. So, okay, so far with the problems that we have worked with, we've been working with regions that are smooth, and that is in between the regions of integration. We don't have any asymptotes, any gaps, any cusps or sharp corners. Typically we call them sharp corners. So check the first example. We didn't have any sharp corner. Good. The second example, another smooth curve, right? Third example, well, we had to set up the problem in two separate integrals because of the intersection that twists the region of integration and changes the order of the top minus bottom situation, right? However, this problem right here is not a smooth curve because of this sharp corner right here, right? So, well, let me show you the hard way to set it up first, and then we are going to change our strategy because, well, you will be doing a homework, you will be given a problem in plain words like this, need to sketch, need to possibly hit the wall, setting up a hard problem, and then find a way around to make it a lot easier, which is what we're going to do for this one. So because of this sharp corner, this is not a smooth curve. We would have to break the problem into two regions of integration. That is area 1, and this whole thing would be area 2. So area 1, or rather total area, that'll be the area of the integral for area 1, which in this case it would be the top minus bottom. That is, top is the square root of x plus 2 minus negative root of x plus 2. And then the second integral would be still the top radical function minus the diagonal line that we have in here, that is x minus 4 dx. Do you see how complicated this problem is? I mean, nevertheless, it's not that bad to compute. Very basic u substitution, you know, but it's kind of scary to work with, isn't it? Is there a way around this? Of course. Of course, instead of setting up two integrals, let me scratch this because we're not going to do this ultimately. And instead, how about we define functions of y this time? Because if we define functions of y, okay, think of rotating this region 90 degrees counterclockwise. You will see a region very similar to the problem we did before, the second problem basically. In that problem, that region won't have those sharp corners within the limits. What am I talking about? Well, first of all, let me define functions of x. I mean functions of y. So this is x equals y squared minus 2, and this is x equals to y plus 4. All right, functions of y this time, and in this case, instead of setting up two different areas, all right, we are going to go from bottom to top. And in this case, I mean bottom to top as far as the limits of integration, but for the region of integration, it's no longer going to be top minus bottom, but rather rightmost minus leftmost, exactly. All right, and along the rightmost minus leftmost and scanning the graph from bottom to top, do you see any sharp corners that require to set up into two integrals? Not this time, right? So that's going to make the problem a lot easier. Well, I really don't want to spend the same time finding the points of intersection. I'm just going to give you these points of intersection. That's y equals to -3. and this is y equals to 2. I mean, we already did this solving the equation a few times. You can verify that later. Put the two equations in terms of y together. That should give you these 2 points of intersection. Okay? So in this case, we are going to set up the integral slightly differently. Area.
Wait, isn't that the y equals to 3 and on the top and y equals to -2 on the bottom?
According to my notes, I have it. You know what? That's true. That's the other way. Never mind. Thank you. Yeah. -2, and this is 3. Yes. For whatever reason, I did them the reverse way. -2 to 3, and so that's the first of all in symbols. That's the integral from c to d, and in this case, not f of x minus g of x. This will be f of y minus g of y. In particular, this will be again rightmost minus leftmost. Okay, and in this case the integral is with respect y, not with respect x. Alright, so let's set up the problem. So what's the rightmost function? Is it the linear function or the quadratic function?
The linear.
The linear, yes, sounds good. That's the integral from, what was that? From -2 to 3 of linear, which is x plus 4 rather. No, not even x. Hold on. Y plus 4. Minus the quadratic function y squared minus 2 with respect y. All right. And well, I mean, this integral looks very similar to one we did before. So that's the area equal to the integral from -2 to 3. That's going to give us -y squared plus y plus 6. And integrating, I mean, the same way. -y cubed over 3 plus y squared over 2 plus 6y from -2 to 3. And well, just to save some time, I will just give you the answer. I'll leave you as an exercise to verify this result. This should be a 125 over 6.